Have you ever looked at an airplane and just wondered how it can be two totally different things at once? How can it be this high-speed bullet way up in the sky, but then become this slow, graceful bird when it comes in for a landing? Well, we're going to break down what the FAA officially calls a complex airplane, and you'll see it all comes down to some absolutely brilliant shape-shifting engineering. I mean, really think about it. It's one of the biggest puzzles in aircraft design. To cruise fast and efficiently, you need a slick, aerodynamic shape that just cuts through the air. But to land nice and slow, you need something completely different, something that can generate a massive amount of lift. So how on earth does a single airplane pull off both? The secret, it turns out, is to make the airplane a bit of a transformer. And the official FAA definition basically gives us the blueprint. A complex airplane has three key systems that allow it to change its very nature: retractable landing gear, flaps, and a controllable-pitch propeller. So let's dive into each one. Okay, first up, let's talk about the wings. You see, a wing that's perfect for cruising at, say, 200 miles per hour would be an absolute disaster for landing at 60. So how did engineers get around this fundamental trade-off? Here's the heart of the problem. On one hand, you've got high-speed cruise. For that, you want a thin wing that creates very little drag. But on the other hand, for landing, you need a really curved or high camber wing to scoop up the air and generate a ton of lift at slow speeds. With a fixed, solid wing, you just can't have the best of both worlds. And the solution is just, it's so clever. Instead of settling for a wing that's mediocre at everything, engineers added a device that lets the pilot literally change the wing's shape in the middle of a flight. These are the flaps. By extending them from the back of the wing, a pilot can instantly increase the wing's curvature, giving it that huge lift capability needed for takeoff and landing. And this isn't a one-size-fits-all kind of deal either. There's a whole family of flaps out there. You've got your basic plain flaps, which are just simple hinges. But then you get to the really advanced stuff like Fowler flaps, which not only curve down but also slide backward, physically increasing the total surface area of the wing for the absolute maximum amount of lift. Pretty cool, right? But, and there's always a but, this awesome performance boost comes with a price, a higher workload for the pilot. Think about landing in a crosswind. That big, extended flap basically acts like a sail. The wind can catch it, lifting the upwind wing, and trying to turn the plane right when you're about to touch down. It demands really precise, skillful control from the pilot to keep the plane pointing straight down that runway. So we've made the wings adaptable, but guess what? The engine and its propeller face the exact same dilemma. How do you build a propeller that's efficient for the massive power you need on takeoff, but also for a steady climb and for a high-speed cruise? This is honestly the perfect way to think about it. A basic fixed-pitch propeller is just like a bicycle stuck in a single gear. It might be great for cruising on a flat road, but it's terrible for climbing a steep hill. It's a compromise that just kills performance in every other phase of flight. And the solution here is the controllable-pitch or constant-speed propeller. You can think of it as an automatic transmission for the airplane's engine. The pilot just sets the desired engine speed, the RPM, for, say, the best climb. Then, a clever device called a governor automatically twists the propeller blades to the perfect angle to maintain that exact RPM no matter what. It's a total game changer. And just like with the flaps, this extra capability means the pilot has more to manage. There's a golden rule for making power changes to avoid putting too much stress on the engine. You can think of manifold pressure as the throttle. So when you want to add power, you increase the propeller RPM first, and then you increase the manifold pressure. When you reduce power, you do the exact opposite. It's a critical sequence that pilots have to get right every single time. And some complex planes add yet another layer of awesome: turbocharging. This system basically recycles the engine's exhaust gas to spin a turbine. That turbine compresses the thin air you find at high altitudes and shoves it into the engine, essentially tricking the engine into thinking it's still down at sea level. This means more power, higher speeds, and way better performance up where the air is thin. Okay, so we've made the wing smarter and the engine smarter. Now for the third and final piece of this puzzle. And this one is all about cleaning up the airplane's shape to make it as slippery in the air as possible. The problem here is just pure, simple drag. Leaving the landing gear hanging out in the airflow is exactly like trying to fly with a small parachute permanently open behind you. It creates a massive amount of resistance that just kills your speed and wastes fuel. So the solution seems pretty obvious, right? Just retract the gear up into the plane after you take off. It cleans up the airflow, lets the plane fly faster. It's a win-win. But this simple solution introduces a huge new risk, a risk that is 100% human. What is it? You guessed it, forgetting to put the gear back down before you land. To fight this, cockpits have really clear indicators. The universal signal that pilots live by is 3 green. It means all 3 wheels, the nose wheel and the 2 main wheels, are down and locked securely in place. Any other combination of lights or no lights at all means the pilot has to stop and figure out what's going on before even thinking about landing. And then there's the final layer of safety. If the pilot is distracted, if they've missed the lights, there's an audible warning. If you pull the power back for landing and drop the flaps, but the gear isn't down, an impossibly loud horn will start blaring in the cockpit. It's an urgent, you can't ignore it reminder to do the most important thing before landing. So let's put it all together. We have these 3 incredible systems, the flaps, that smart propeller, and the retractable gear. And yeah, they dramatically boost the airplane's performance, but they also dramatically increase the demands on the person sitting in the cockpit. This list, which comes straight from the FAA, tells you everything you need to know. The most common and most expensive mistakes with these airplanes aren't usually about something breaking. They're about the human factor, about memory, attention, and following procedures when you're under pressure. And this really brings us to the most important point of all. The technology is only half the story. As the FAA themselves put it, a pilot has to develop the knowledge and judgment to fly these planes well. It's not something you can just pick up. It takes dedicated, serious training. So that's what really makes an airplane complex. It's not just the fancy hardware. It's the marriage of these clever systems with the human skill required to manage them. And it kind of leaves us with a final question to think about. As our cockpits get more and more automated, filled with more screens and computers, what are the core skills that it will take for a pilot to truly master the machine? Thanks for tuning in for this explanation.